In this video, we're going to examine the stereochemistry of cyclohexane, and we're going to look at the various conformations it can undergo. Now, we've already talked about the ability of that chair conformation to flip from one chair to another chair conformation. And what we're going to do in this video is we are going to envision this process by step by step, pulling one side of the chair up and then pushing the other side down. And we're going to look at the energy associated with all of those various conformational changes. Okay? And so first off, we need to think about, again, how to draw the structures. So we're going to start off with cyclohexane in this particular conformation. And I'm going to number it 1, 2, 3, 4, 5, 6. So carbon number 1 is the farthest carbon on the left. Now, what am I going to do? Well, I'm going to take carbon number 1 and I'm going to push it up. I'm going to start to push it up, right? Because even though cyclohexane doesn't have free rotation, it has flexibility. So I can start to push carbon number 1 up. Now, as I push it up, what happens? Well, it takes on this conformation where now essentially I like to think of this as a reclining chair. This is actually called a half chair, right? A half chair, where basically the legs of my chair are starting to swing up, okay? Now, in this conformation, notice that I have a lot of eclipsed bonds now, right? So if I take a look, the 5, 6, 1, 2, and 3, all of those carbons have carbon-hydrogen bonds that are eclipsed to one another. And therefore, this is going to require a lot more energy. It's going to require energy to go from the chair conformation into this half chair conformation because now I'm increasing the torsional strain of my molecule, right? So, but notice when I'm going to keep going and I'm going to push carbon number 1 up again, and when I do so, I get a new conformation. And this conformation is called a twist boat. So a twist boat. Notice I'm trying to keep track of all of the carbons, so I'm numbering the carbons as I go along. So now 1 is completely up. I'm still looking at that bond angle there. 2 is kind of pushed down a little because the whole thing twists a little bit. And then I have that 3, 4, 5. Notice that bond angle hasn't changed much. And 6 has twisted up just a little bit. Okay, so now the C2-C3 bond and the C5-C6 bond are not parallel to one another. That's why we call this a twist boat, right? So that's very important to understand. All right, so now what am I going to do? Well, I'm going to take that twist boat, I'm just redrawing the whole thing. I'm going to take that twist boat and I'm actually going to force that C2-C3 bond and the C5-C6 bond to be in the same, to be parallel to one another. And when I do that, what happens is carbon number 1 and carbon number 4 actually get pushed together, closer together. And the end result looks like this, okay? Where I have C1, C2, 3, 4, 5, 6, right? I'm numbering my system again. So now C1 is pointing up, but C4 is still pointing up at me. And if I think about this structure, it's called a boat, right? It's a boat structure. But the key to the boat structure is that it actually requires a little bit of energy to go from the twist boat to the boat. And the reason for that is since I'm pushing C1 and C4 closer together, they both have hydrogens associated with them, and there is some steric hindrance there based on the hydrogen atoms interacting with one another. So there's going to be an energy associated with that steric hindrance. So I have to add energy to overcome that steric hindrance. Well, now I can, you can think about, in terms of equilibrium, the twist boat being either one direction or the other direction. So I can twist it, all right, to alleviate the steric hindrance. I can twist it in the other direction now, where there's another twist boat, right? Another twist boat conformation. And I have C1, 2, 3, 4, 5, and 6 carbons, drawn as such. So I'm trying to help you keep track of where all the carbons are. So I'm labeling all of the carbons. And hopefully, again, you have your model kit and you can kind of follow along what we're doing here. So now I have a twist boat. You can envision where C1 is, where C2, 3, and 4, and 5, and 6 are. And now what I'm going to do is I'm going to take C4 and I'm going to push it down. So essentially I'm taking one side of the molecule, pushing it up, and then I'm going to take the other side and push it down. What happens when I push C4 down? Well, I end up getting a half chair, another half chair conformation. And again, we know that it's going to require energy to do so because we have so many carbon-carbon eclipse bonds. So this is going to be a high transition state conformation. And then as I push C4 down even further, now I can take on the other conformation, chair conformation, where I have, C4 now is pointing down, C1 is now pointing up, and now everything is, that was pointing down is pointing up, and everything that was pointing up is now pointing down. So basically that's what is happening when you go from one conformation to the other, when you flip chair conformations. And keeping track of all the carbons becomes vitally important. Now, the thing that we can do about this is we can actually plot a conformational potential energy diagram based on all of the various conformations. And we see when we do so, the energy diagram looks something like this. Now, what are all of these various hills and valleys associated with? Well, obviously the chair conformation has no strain. It's going to be the lowest in energy. So we're going to start at the initial chair conformation. Now, as I go from chair to half chair, I have to add a lot of energy because now I have that torsional strain, all of the eclipse bonds associated with it. As I move C1 up even further and the molecule twists a little bit, I'm alleviating all of the torsional strain. Well, most of the torsional strain, I should say. There's still some eclipse bonds associated with it. And so it goes down to a lower energy level, but notice not as low as my original chair conformation. So now I'm gonna twist it so that the C2, C3 bond and the C5, C6 bond are parallel to one another, giving me that boat conformation. But what happens when I do so? I have to add a little bit of energy to overcome the steric hindrance between the carbon-hydrogen bonds of C1 and the carbon-hydrogen bond of C4. So now I can twist the other way, which alleviates that strain, and I get my other twist boat. And now when I start to push that C4 down, I then go back into a half chair conformation, which requires energy to do so, again because I'm increasing the torsional strain, until eventually upon pushing that C4 down even further, I get to my last, other chair conformation. So going from one chair conformation to the other chair conformation requires this oscillating energy to occur. And of course we can measure the energy. So the energy associated going from the chair to the half chair requires a lot of energy, right? Because I'm going from no strain to a lot of torsional strain, and that energy is about 10.8 kilocalories per mole, so around 11 kilocalories per mole. And then I can alleviate that getting to the twist, but notice the twist is still higher in energy than my chair conformation by about 5.5 kilocalories per mole because it still has torsional strain associated with it. And then of course notice I have to add a little bit more energy relative to that twist boat to get to the boat, right? Because of the steric hindrance, and it's a little amount, but certainly enough to make a difference, right? And then we proceed down to the other side. And so this hopefully gives you a you know a good picture about what's really happening in that molecule. Now, that 11 kilocalories per mole. So that is the amount of energy you need really to go from one chair conformation to the other chair conformation is 11 kilocalories per mole. And at room temperature, this is a fairly easy process to do. And therefore, cyclohexane at room temperature is basically going from one to the other, back and forth and back and forth. It's flipping, it's ring flipping, right? It's undergoing conformational changes at a rapid pace, as a matter of fact, something like 10 to the 6th times per minute or something crazy like that, okay? But hopefully this paints a picture, a big picture about that whole process taking place. So practice drawing all of those conformational changes because you might be asked to do so later on.